Here we are looking at the formulas for the definition of the derivative using limits. So if we look at these two different formulas, we can see that they are very similar. However, there is one main difference between them. So the first one that we have on the left, we have the limit as h approaches 0 of f of a plus h minus f of a over h. So if we notice this one, this contains an a. Okay, if we look at the second one, we have the same exact thing, but the difference here is that we have an x instead of an a. So for this first one, when we have an a involved, the a is a particular point. So that's a particular x value. So if we're using this type of format, this is finding the derivative at just one point. So it's one point at a time. In the problem, they will give you the specific point that you're trying to find the derivative of. But whenever we have the a there, that means that our answer is going to be a number. It is the limit at a particular point. When we're looking at the function on the right, because it has an x involved and not an a, this is a function that's representing all solutions. So it representing all solutions. So what that means is that there are infinitely many points that are contained in that formula. So when we want just one point, we have the a, and when we want the entire function, we have the x. So here is the main definition of the derivative of a function. So notice that we have the x here. Okay, so this is just if we're trying to find the derivative of a function and we want it as a function itself. Notice the notation here as well. So f prime of x, that's how we pronounce that. So I'm just going to write it f prime of x. So that is the derivative. What this is this is the derivative at x. So instead of being at a point, this is just at x. So we're going to have x in our answer. It is just going to give us a function. So I'm just going to write that down so we have it. So derivative at x. And what that actually is giving us is the function for the slope of the tangent line. So we talked about secant lines versus tangent lines in a previous lesson. When we're trying to find the slope of the tangent line to a curve, what we're really doing is we're finding the derivative, and usually we're going to plug in a certain point, but if we wanted just the function of it in terms of x, we would use this. So we're going to look at an example of how we actually use this limit definition. So given f of x is equal to x squared, use the definition of the derivative to find f prime of x. So notice there's no number, there's no like point we're plugging in, we just are trying to find the function. So we're going to use our limit as h approaches 0 of f of x plus h minus f of x over h. So we're going to plug this in. So if you remember function notation, basically what we're going to do here is we're going to take whatever's in the parentheses and plug it in for x in our function. So x squared is the function, so we're going to plug in x plus h. So I'm going to have x plus h squared, and then I'm going to subtract f of x, so I'm plugging x in, so that's x squared over h. Now what we need to do is expand the x plus h squared. So remember, when you're squaring a binomial, you can't just distribute the exponent. We need to actually write out x plus h times x plus h and FOIL it. So if we do that, we get x squared plus 2xh plus h squared. And then we have this minus x squared at the end over h. So if we simplify this a little bit, we can see that the x squareds are going to cancel out. So we end up with 2xh plus h squared over h. Okay, and then from here, if we try to do our normal limit routine where we plug in 0 for the h, we're going to get 0 in the bottom. So we want to keep going and we want to keep using algebra until we can kind of cancel things out. So if we look at the numerator, there's an h in common, so I can factor out that h. So I have 2x plus h over h. These h's are going to cancel each other out. So I have the limit as h approaches 0 of 2x plus h. So now I plug in my 0 for h, and I end up getting 2x. So that is what f prime of x is. So f prime of x is equal to 2x. It's what we get after we use our algebra, simplify stuff, and plug in the 0. Okay. So we're going to look at one more. Now, if we look at this example, we have f of x is x cubed minus x, and f prime of x is equal to 3x squared minus 1. Use the definition of the derivative to find f double prime of x. So if you see this double prime, that means that we're going to be finding the second derivative. So 1 prime is the first derivative, 2 is the second. You can have higher derivatives. So if I had the third derivative or the fourth, you would see a little number 3 or 4. So you use the prime marks up to 2, and then you use the number that you're trying to find after. So for time purposes, if we did the limit definition of the derivative one time for f of x, we would get this answer for f prime of x. Okay, so you can do it to double check, but that's what it is. So we end up here. So now if I wanted to find the second derivative, I'm going to do the limit definition of the derivative for the first derivative. Okay, so really we're doing it twice, but for time, we're not doing it the first time. Okay, so I'm just giving you the answer. So now, very similar to what we did before, okay, we're using this as our function now because we're assuming we did it once already. So now if I want to find f double prime of x, which is my second derivative, I'm going to do the limit as h approaches 0, and I'm still using my definition of the derivative for the limit here. So this is my basic skeleton that I'm using here. And now I'm just going to plug in. So I'm just going to make more space here. So limit as h approaches 0. So again, we're going to take x plus h and we're going to plug that in for where we have this x. So I'm going to have 3 parentheses x plus h squared minus 1. And then I'm subtracting f of x. So I'm subtracting the entirety of the 3x squared minus 1. So if you notice, I put it in parentheses. So I have to make sure when I go to subtract, I distribute my negative to both. So putting it in parentheses kind of helps you remember that. And then the denominator we have here is h. So again, similar to before, you have to FOIL out the x plus h squared and then distribute the 3. So I'm just going to jump to what that is. But if you need to write it out, by all means write it out. So you're going to FOIL the x plus h first and then distribute that 3 in. So this is going to give us 3x squared plus 6xh plus 3h squared. Don't forget to distribute this. So we're going to have negative 3x squared plus 1 over h. And when we look at this, we can see that the 3x squareds are going to cancel out. And oops, I forgot this. Minus 1 over here, sorry. So this minus 1 I left out. My bad. Okay, so the negative 1 here and this positive 1 here cancel out. This 3x squared and this negative 3x squared cancel out. So I have the limit as h approaches 0 of 6xh plus 3h squared over h. Similar to the previous problem, I'm going to factor out my numerator. So I'm going to take out that h. So I have 6x plus 3h over h. These will cancel out. So now if I plug 0 in for h, I'm going to end up getting just 6x. So I'm just going to write this up here. So f double prime of x is equal to 6x. So my second derivative is equal to 6x.